Hello everybody, welcome again, and this is Jim Corkins. We are continuing on with momentum, and this is our last part in momentum. It's 6.2 collisions in 2D. If you haven't done the reading, please do so. Those readings are indicated in your Canvas course. Now, we had talked about how these are the useful equations for this section of energy and momentum, so please keep a hold on them. Again, here's the list of all the different types of energies. This is the starting part, and here's the list of all the different types of energies. For momentum, you have the basic momentum equation, you have the definition of impulse, you have the change in momentum plus or minus impulse, and you have the coefficient of restitution equation. So all of these are going to be helpful for the energy and momentum part of our class. All right, well, let's get to where we need to start with. So momentum, linear momentum, is not just a one-dimensional quantity. It is actually in 3 dimensions, x, y, and z. But we are going to be doing just the 2-dimension part of that. So when the momentum is changing in the x and the y directions simultaneously. Okay, so that means you're going to have to know your trigonometry, and we're going to be doing sines and cosines and things like that, and tangents to find angles. All right. So if you are still a little rusty on that stuff, or you feel like might have got a little rusty on that, please review it. That is in section 2.0, trigonometry review. All right, moving on, let's go ahead and do an exercise. Okay, so in this exercise, and this is a basic part, where you have a ball that is moving at 8 meters per second, is 2 kilograms, and is moving at an angle of 30 degrees. What is the ball's momentum in the x and y direction, and what is its overall momentum? Okay, so not only should you calculate its momentum in the x and y direction, but also figure out the overall momentum. Okay. All right. Go ahead and try this out and pause the video now. Okay. We are back. So to start with, I gave you a little object, so we're going to give this 2 kilograms. In fact, I think what we should do is lay down a coordinate system. I like doing that whenever I have to work with vectors, especially in 2 dimensions, and I think this is going to help us out. So again, we're going to try to get in the habit of laying down the coordinate system in the x direction and the y direction, just like we did with force diagrams. Okay, really anytime you're working with 2-dimensional vectors, this is what we're going to do. So negative y direction. Okay, so they're giving us that this is a 2 kilogram object, and it's moving. It's got a speed of 8 meters per second initially, and it's traveling at an angle of 30 degrees. Okay. All right. Well, in the x direction, let's go ahead. We're going to have to take this velocity and figure out the x and y components of this velocity vector. So right here, we're going to take this vector, which is the addition of 2 vectors, a vector going to the right, and yeah, let me just use black for that, a vector going to the right, and when we add to that, the vector going upwards. So when we add those 2 vectors together, what we're going to do is we're going to take, so the side touching the 30 degrees is this horizontal side. So that will be 8 meters per second cosine of 30 degrees. and that'll be to the right. Upwards, it's going to be positive 8 meters per second sine of 30 degrees. Okay. All right. Well, we're going to do 3 things. We are going to figure out the overall momentum. We're going to figure out the overall initial momentum, which is the overall momentum. We're going to figure out the momentum in the x direction and the momentum in the y direction. Okay, so the overall momentum, pretty easy. You just take the initial velocity that they give you, and which is going to be 2 kilograms times the overall velocity, which is 8 meters per second. So this is going to be 16 meters per second. Since that velocity is at a diagonal, this is neither plus or minus. Okay? It's just a number. Okay? Just like our vector addition in 2 dimensions. Okay? But it does become plus and minus when we break up this diagonal to our coordinate system. So what we're going to have is the initial momentum in the x direction. That is going to be equal to the 2 kilograms times positive 8 meters per second cosine of 30 degrees. So that initial momentum in the x direction, let's go ahead and figure it out. That's 0.866 times 2, 17.32, 1.732. So this is going to be positive 1.732 meters per second in the x direction. In the y direction, we are going to do the same thing. We're going to take 2 kilograms, but this one we are going to multiply by the vertical component, or the y direction velocity, which is 8 meters per second sine of 30 degrees. The sine of 30 degrees is a half, so the initial momentum in the y direction is going to be 16 divided by 2, which is going to be positive 8 meters per second. And I should put kilogram meter per second in front of these. Sorry. Got to make sure I use the proper units. So since we're dealing with momentum, we can't forget the mass. And kilogram meter per second. Okay. So this is how we do the basics. This likely you're going to be given a vector, a velocity vector at a diagonal, and at some point you're going to have to calculate the x and y components of that velocity vector. So this is the basics of it. Okay, and if we had to figure out if you were given the x and y components of this and you had to calculate the overall velocity, well, that's just c squared. C squared equals a squared plus b squared. So that 8 meters per second, which is the hypotenuse, so applying Pythagorean's theorem, we'd have to take the x direction component, positive 8 meters per second cosine of 30 degrees. So this is what to do if they asked for the overall velocity and they gave you the x and y components. You would have to just do this. So you just have to take those x and y components and take the squares of those. To calculate the overall, which is 8. Okay, so they might give you the overall velocity and an angle, and you have to figure out those x and y components. Or they might give you the x and y components, and you have to figure out the overall velocity, and you have to figure out the angle. To figure out the angle, you would just take theta of 30 degrees, and you would take the velocity which is opposite, which would be v sub y, v initial y, I should say. And we just need the magnitudes of those, and v initial x. Okay, so you do the inverse tangent, and the y part would be positive 8 meters per second sine of, well, which would be, they would just give you a number. So this would be positive 8 meters per second, and again, this is positive 1.732 meters per second. So they would give you, it's traveling at 8 meters per second in the y direction upwards, and 1.732 meters per second in the positive x direction, right? And then you would calculate it this way. So this is how to do these type of problems. You're going to have to go back and forth, right? All right. Okay, let's move on to our first two-dimensional problem where there's an actual collision happening. Now, in a way, this is kind of a review of 6.1, but just really simplified, okay? Now, in this problem, we have a 2 kilogram bouncy ball that is traveling at 4 meters per second. It's 2 kilograms. It's going to hit a wall, and it's going to bounce with a perfectly elastic collision. Well, if it's a perfect elastic collision, and there's only one object, the speed is really not going to change. It's just going to be the directions of some of those velocity vectors. So for example, we know over here it's traveling at 4 meters per second at this angle. When it bounces and there's a perfect collision, that means there's no change in the overall energy. Well, 1/2 times 2 kilograms times 4 meters per second has to be equal to 1/2 times 2 kilograms times 4 meters per second, which means this incoming angle is equal to that outgoing angle. So we've kind of already just reasoned through this, okay? And that's going to be important because we need to figure out what the impulse is in the x and y directions, okay? So let's do this. Let's lay down a coordinate system since we're going to be dealing with vectors. And let's do the initial momentum. Okay, so we're going to do the initial momentum, and then let's lay down a coordinate system for the final momentum. So this is positive y, positive x, negative y, negative x. Okay, so this is initial, and this is final. Okay, well, the ball initially, it's a 2 kilogram ball. It's initially moving up and to the left, and they're giving that angle right here of 45 degrees. And the speed is 4 meters per second. Okay, that means its velocity, that's the resultant vector. It's a resultant of an up vector added to an x direction vector. So this, if we look at it, I'm going to zoom in a little bit. This is going to be to the left, 4 meters per second. You know what? I think I need a little bit of room. So this is going to be negative 4 meters per second cosine of 45 degrees. And this upward one is going to be positive 4 meters per second, because it's pointed upwards, sine of 45 degrees. Okay? After the impact, it's moving up and to the right now at 45 degrees. So now this is the angle 45 degrees, and this is 4 meters per second. So this is going to be positive 4 meters per second cosine of 45 degrees. And this is going to be positive 4 meters per second sine of 45 degrees. Okay? All right. Well, that's how it's laid out, the initial and final conditions. So you have to have that laid out just like you normally would in the other problems, where you have an initial case and then a final case. All right. Well, we already know the final velocities afterwards. Let's go ahead and go through the process of figuring out what the impulse is done on the wall to the 4 kilogram ball, to the 2 kilogram ball. So the initial momentum in the x direction is 2 kilograms times negative 4 meters per second cosine of 45 degrees. We don't know the impulse, so we're just going to leave it in here. And then after the collision, it's got 2 kilograms positive 4 meters per second cosine of 45 degrees. Okay? In the y direction, it's got a 2 kilograms times a positive 4 meters per second sine of 45 degrees plus impulse and that's going to be equal to 2 kilograms times positive 4 meters per second sine of 45 degrees. Okay. Let's start calculating some numbers. So this is going to be 45 degrees, trigonometry, cosine, 0.707 times 8 equals 5.66. So this is going to be equal to negative 5.66 meters per second in the x direction, and this is going to be a positive 5.66 meters per second in the x direction. So that's what we're going to be computing for the x direction. In the y direction, I know sine and cosine of 45 degrees are both 0.707, but I'm just putting in the calculator, so don't judge me. I could hear you judging me. So times 8 equals 5.66. So this is a positive 5.66 meters per second in the y direction, plus the impulse in the y direction, which is equal to positive 5.66 meters per second in the y direction in the end. Now to calculate the impulse, if you look at this, its speed in the y direction isn't changing. Okay, well, its velocity in the y direction isn't changing, but its velocity in the x direction is tremendously changing. It's moving to the left, and now it's moving to the right with the same velocity that it came in at. So we're going to take this negative 5.66 and add it to the other side. When you do that, you're going to get this. So the overall impulse in the x direction supplied by the wall against the 2 kilogram ball is 5.66 plus 5.66, 11.32. So this is going to be a positive, and I'm missing units here. Keep doing that. I'm doing that today and it's bothering me. I have to squeeze the units in here. This should be kilogram meters per second, and this should be kilogram meters per second. This should be kilogram meters per second. This should be kilogram meters per second. I sound like Oprah. You get a car. You get a car. Boy. It's going to be amazing if you learn anything in my class. All right. Moving right along, and I've totally forgotten this number. 5.66 plus 5.66, 11.32. So the impulse supplied by the wall to the 2 kilogram ball is 11.32 kilogram meters per second, or positive 11.32 newtons times a second. So if we knew the period of time of that impulse, which would be like a very small number, like 0.001 or 0.0001, we could figure out the force. All right, in the y direction, well, we have to subtract this negative 5.66 kilogram meters per second momentum onto the other side. Minus 5.66 kilogram meters per second. So, as you can see, in the y direction, the ball does not supply any impulse. It supplies no force in the y direction. Okay? So this is the basics of two-dimensional motion with one object. Okay? All right. Let's move on to another problem. Okay? In this problem, we have a ball that is 0.5 kilograms. It's shot at an angle of 30 degrees with an initial velocity of 14 meters per second. It's going to rise up to a height of 2.5 meters. And it's going to impact this 4 kilogram ball, and it's going to do it in an elastic collision where it's going to push the 4 kilogram block to the right with some final velocity, and the 4 kilogram block is going to push the 0.5 kilogram ball to the left after the impact. Okay, and so this is one of those problems where there's energy and momentum that are playing off of each other, okay? And we have to figure out what is going on, okay? And so we could supply these final velocities. And we're going to assume this is a perfectly elastic impact, okay? All right. Well, first thing that we're going to have to do is we need to figure out the overall velocities in the initial velocities in the x direction and the y direction, right? Okay, so this ball is moving to the left at it will be moving to the left at positive 14 cosine of 30 degrees, and moving upwards, these are its initial velocities in the x and y directions of positive 14 cosine of 30 degrees. So those are the velocities. Okay. Now, when it rises up to this height of 2.5 meters, we need to figure out what its velocity in the x direction is after this shot. We need to figure out its velocity in the x direction, and we need to figure out its velocity in the y direction. So this is going to be vy middle, and this is going to be x middle. Okay, so I think that's where the energy part is going to come into play. Okay, so this is a projectile motion problem. As we know, the velocity in the x direction for the middle part has to be equal to this positive 14 cosine of 30. And we just need to figure out, does it have a velocity in the y direction when it gets to this maximum height? Because that means if it does, it's actually going to be traveling up like this when it hits. So let's use energy to figure out the y components of this. All right. So this part, figuring out if it has a velocity in the y direction, is going to be over here. We're going to have to do this. So let's go ahead and figure out it. So it has an initial kinetic energy, okay, which is going to be, and we're actually only going to take this part right here, the 14 sine of 30, okay. So let's figure out what its final kinetic energy is when it gets to that height of 2.5 meters. I'll show you what I mean. So it's being launched at a height of 0. So it has no potential energy in the y direction. We're assuming it's launched, and so let's look at the energy after it's been fired. So since it's only flying up, there is no outside forces or work. It's just a change of kinetic energy to potential energy, or possibly another kinetic energy. So now we are asking the question, does it have a kinetic energy in the y direction? Okay, so we are just determining, does it have this? Does it have a velocity in the y direction after it's fired? Okay, so it's getting to that height and no springs are touching it. So what we're going to have, initial velocity in the y direction squared. We're asking the question, does it have this? Does it have a kinetic energy final? Let's just keep it simple. And this ball is getting to this maximum height, to a height of 2.5 meters. We don't know if that's the maximum height. All right, so let's go ahead and plug in our numbers. Hopefully this energy will be equal to this energy, and if that's true, the kinetic energy will be 0. So this is going to be 1/2 times 0.5 kilograms times the initial velocity in the y direction. And that will be positive 14 meters per second sine of 30 degrees squared, plus the final kinetic energy on the other side. And this is what we are asking. Does it have a final y direction kinetic energy? Well, let's put in our potential energy, which is going to be 0.5 kilograms times 9.8 meters per second squared. I'm going to scooch over. I'm going to zoom out a little bit. And times 2.5 meters. Okay, let's start calculating. So this is going to be, actually, what am I doing? This right here, 14 sine of 30, that is just 7 meters per second, right? Sine of 30 is a half. This is 14. So what we're going to do is we're going to take 7 squared, which is 49, times 0.5 times 0.5. 12.25 joules. So the initial energy is 12.25 joules. Hopefully, because I want the problem to be simple, this end potential energy is also 12.25 joules, which we'll figure out. 2.5 times 9.8 times 0.5. 12.25 joules. Phew! So we just determined that just the y direction component of the kinetic energy gets totally consumed and turned only into a height, such that when it gets up to that maximum height of 2.5 meters, all of its kinetic energy is consumed. So what that means is when it's right here, now that it's at that height, okay, it's just traveling in the x direction, okay? Which means we don't have to worry about the momentum in the y direction. Well, we can. We're going to do some neat stuff with this. But let's go ahead and figure out the velocity in the x direction. So what we're going to do is, we know right now it's only got a velocity in the x direction. So now we know that ball, which is 0.5 kilograms, is traveling to the right at positive 14 cosine of 30 degrees. And this is the velocity that we're talking about. It's the same velocity here, and it's the same velocity here. So they're all the same velocity. So I'll just put x right there. So I'll put VIX. Since, again, in projectile motion, its velocity doesn't change. All right. Now, the block, what we're going to do, we're making our little storyboard. The block, which is 4 kilograms, it is not moving. After the impact, it's going to have a velocity in the x direction. Which is probably going to be to the left. And I'll put 0.5. And then we need to figure out the velocity in the x direction of the 4 kilogram block. The final velocity, 4 kilograms. Okay? I need to grab that coefficient of restitution equation. Hold on a second. Since we have 2 unknowns and 1 equation, we really can't do this problem without employing the energy during the collision of just the collision in the x direction, or using the coefficient of restitution. Okay? So let's go ahead and multiply this out, and then we'll create that equation for the coefficient of restitution and set it equal to 1, since it's a perfectly elastic collision. So 30 degrees cosine times 14 equals 12.12. So just a little bit over, I'll write 12.124 meters per second. So its initial momentum is going to be 0.5 kilograms times positive 12.124 meters per second. This is just 0, and this is 0.5 kilograms V final, and I should just put a half. That'll look a little bit better than that thing. V final, a half. So that's a half kilogram plus 4 kilograms V final 4. Now for the coefficient of restitution, again, it doesn't matter the order in which you do this. You just got to make sure you're consistent. So if you start off with the initial velocity for the first object, final velocity for the first object, start off with the initial velocity for the first object. So we're going to construct this. So that coefficient of restitution equation right here is going to be E, which is going to be equal to 1, which is going to be equal to, I'm going to circle this and leave it off to the side. This is going to be, let's start off with the final velocity for the 1/2. So I'm going to put a negative V final a half minus V final 4 kilograms. Here's going to be the initial velocity for the half guy, which is going to be 12.124 meters per second, just positive, minus 0 meters per second. Okay, so I scooch the screen over. Okay, so let's go ahead and we're going to multiply both sides. And I'm going to just get rid of this so it makes more sense here. This is E. Both sides by 12.124. And when you do that, you get 12.124. This negative is going to stay here. In fact, it's going to kind of look like this. V final a half minus V final 4. Okay, and we're going to multiply that negative through. Okay. In fact, let's just multiply both sides by the negative. Okay. And if we do that, we're going to get V4 1/2 minus V final a half minus V final 4. And then we're going to add that 12.4 meters per second. I should have had the units on this. Meters per second. Plus the V final 4. We're going to add this to both sides, and that is going to be V final a half. Okay. So this is going to be our equation that we're going to sub into. We're going to sub this into our momentum part that we were doing. We're going to sub it into right here. Okay. Okay. Now, 12.124 times a half. Divided by 2, 6.062. So this is going to be positive 6.062 meters per second. Now we're going to put our 0.5 kilograms, and we're going to multiply both sides by this negative 12.124 meters per second plus V final 4. And then add to that the 4 kilograms V final 4. Okay, now we have to multiply this 0.5 kilograms through. And when we do that, we're going to get a negative 6.062 kilogram meters per second. And I forgot the kilograms over here again. Kilogram meters per second. Kilogram meters per second. Plus 0.5 kilograms V final 4 plus 4 kilograms V final 4. We're going to add this onto the other side, and when we do that, we're going to go back to 12.124 kilogram meters per second. So we're going to add that guy, and let's add these two together. 4.5 kilogram V4 V final 4. So now we just have to divide both sides by this, 4.5 kilograms, which is going to be V final 4, which is going to be, I don't know, we'll find out. 12.124 divided by 4.5. 2.69. So that 4 kilogram object is going to be moving to the right at 2.69 meters per second. Now that we know that, we could figure out the final velocity of V4 final. So we're going to take this number and we could use either equation. We could plug it back into here, and I'd rather this is already set up. So I'm going to plug it in to right here. And when we do that, we're going to get the negative 12.124 meters per second. And I'm going to highlight this. Plus 2.69 meters per second V final a half, and we're going to have to do that subtraction. 12.124, which is going to be negative plus 2.69, negative 9.434. Negative 9.43 meters per second. All right. So here's how you do those more complicated problems. Again, if there's an elastic collision, just make sure that coefficient of restitution equation is handy and ready to go. Okay. And again, this is one of the more difficult problems. All right. Not the type of problem that you would regularly run into in this stuff. Okay? All right. Let's move on to the momentum. So just basic momentum problems with elastic collisions and inelastic collisions with two objects in 2 dimensions. Okay? So we're going to start off right here. Okay. So here we go. We have a problem where they basically say we have a 2,000 kilogram. I'm going to zoom in on this. We have a 2,000 kilogram Cadillac, and it looks like it's moving in the positive y direction at 3 meters per second. Okay, it's going to impact a Volkswagen, which is 1,000 kilograms, moving to the right at some unknown speed. And what they say is, after the collision, well, when they make that collision, it's going to make an angle, and they're going to stick together at 35 degrees. Okay? So the police officer measured that angle. And so, and it's the Volkswagen driver is accusing the Cadillac driver of failing to stop. So we have to figure this out given the information. So the Cadillac driver is heading north at 3 meters per second. And it's 2,000 kilograms. And actually, I'm sorry, the Volkswagen driver is being accused of failing to stop. After they hit, they're going to combine masses and be moving off at 35 degrees. Okay, so you have to approach this as if they are two separate problems, well, one for each one of the directions. Okay, so let's start off with the initial momentum, okay, in the x direction. And if you look at the initial momentum in the x direction, the Volkswagen has a velocity in the x direction, but the Cadillac driver does not. So it has 0 velocity in the x direction, but the Volkswagen has a velocity in the x direction to the right. Okay? So let's go ahead and plot that out. So the Volkswagen, I'm going to put first, it's 1,000 kilograms. And it's got a velocity in the x direction. And I'm going to put just a W there. So the velocity wagon, Volkswagen. The Cadillac has no velocity in the x direction. So this 2,000 kilogram object has 0 meters per second in the x direction. Now, after the impact, both objects are going to be stuck together, and that's going to be 1,000 plus 2,000 kilograms, traveling at some velocity in the x direction. Okay? Which we're going to have to figure out. Okay? We'll develop that velocity in the x direction based off of this vector description. In the y direction, okay, now before the impact, only the Cadillac had a velocity in the y direction, and that was positive 3 meters per second. So it's the only thing that has momentum in the x direction. The Volkswagen has no momentum in the y direction. Only the Cadillac does. So in the y direction, the Volkswagen, which is coming first in both problems, has 0 momentum in the y direction, but the Cadillac has a positive 3 meters per second upwards. So after the impact, again, they're going to be stuck together, 1,000 plus 2,000 kilograms, moving at some final velocity in the y direction. Okay? Now, what I'm going to do is I'm going to take that picture, right? So here's our two guys, and this is 3 kilograms. 3 kilograms. So I'm just going to put a 3 here. And I'm going to create my coordinate system. And I'm going to just do this with a solid green color. And I need to use this, I'm going to be analyzing this final velocity. So this is positive y, this is positive x, this is negative y, this is negative x. And you could probably do this without being so detailed as I am, but I'm just making sure I teach you what I know. So this is the final velocity. This is the overall final velocity. We know this angle is 30 degrees. So this velocity in the x direction which is v final x. That is v final cosine of 30 degrees. This velocity upwards is going to be, and that should be positive. This will be positive v final sine of 35 degrees. I've got to be careful. That's at 35 degrees, not 30. So we are going to replace these two values with this stuff. V final y. Okay. So this guy's momentum, the Volkswagen's momentum, is going to be 1,000 kilograms VW, and that's plus 0, which is going to be equal to 3,000 kilograms times V final cosine of 30 degrees, 35 degrees. Okay, so this is going to be important. We're going to need that. Okay. Now over here in the y direction side, this is going to be 0, so this is going to be positive 6,000, 3 times 2,000 kilogram meters per second upwards, and that's going to be equal to 3,000 v final y sine of 35 degrees. So this is what we're trying to find. And we cannot find it because we need to figure out what v final y is. Well, v final is, and this should just be v final since I took the y and I took the sine of 35 degrees. So this is just v final sine of 35 degrees. So since we don't know what v final is, let's use this equation to figure it out. So what I'm going to do is I'm going to divide both sides by 3,000 sine of 35. So just do that together. 6,000 kilogram meters per second divided by a total of 3,000 kilograms sine of 35 degrees. And that is going to be equal to, oh boy, let's go 6,000. Actually, I'm going to put v final right here. So v final is going to be equal to 6,000 divided by, I'm going to do the 35 second function sine. I'm going to multiply that by 3,000 in parentheses equals. Equals 3.4, let's say 3.49. So 3.49 meters per second. I'm going to do that really quick again just to double check my answer. I'll be right back. I double checked it and it's correct. So what we're going to do is we're going to take this guy, this 3,000, positive 3.49 meters per second, and we're going to plug it right into here. Okay. So now what we're going to get is 1,000 kilograms VW, which is the initial velocity of the W guy. I should put an I there just to be clear. 3,000 kilograms times 3.49 meters per second times cosine of 35 degrees. So I'm going to write that down, times 3.49 meters per second times the cosine of 35 degrees. Okay? So the VWI is going to be equal to this whole thing divided by 1,000 kilograms. So the initial velocity of the Volkswagen, whew, this can be a lot. Okay, so let's do the 35, and I'll put this over here. Back up a second, that should be 35 cosine. We're going to multiply that by 3.49 times 3,000 equals, and we're going to divide that by 1,000. 8.58. So the Volkswagen was traveling 8.58 meters per second. And that is this problem. Okay. So with inelastic collision problems, likely you won't need to use energy stuff unless you're specifically asked to. Like you have tested in my tutorials, but this is a good example of how to do a 2D collision problem. Okay, now you have one similar to this in your tutorials, so you could approach it a similar way. Yours is easier though. Actually, I think I give you the initial velocities of these two guys, and you have to figure out the X direction and Y direction guys of those, and the overall velocities and the angle. So it's kind of the reverse of this. Much easier. All right, let me show you how to do a two-dimensional elastic collision problem. Okay. So this is our last problem for this section. Now, elastic collision problems in 2 dimensions can be difficult. Okay. Luckily, you will experience problems that you'll probably have enough information so it doesn't become too bad. Here's the problem. This ball is moving to the right, and it's 0.5 kilograms. It's moving to the right at 4 meters per second, and it's going to hit a 0.3 kilogram ball that is at rest. Once they hit, after the collision, the 0.5 kilogram mass is moving upwards and to the right at 2 meters per second at an angle of 60 degrees. And they want to know what the 0.3 kilogram mass is moving at for its overall final velocity, which is this. Okay? And we need to figure out that angle beta. All right, so let's do this problem just with a similar approach that we did with this problem. We're going to approach those two momentums as if they are two separate things. Okay? All right, so here's the initial momentum of ball A, which is 0.5 kilograms, and we're doing the momentum in the X direction, and it's moving to the right at positive 4 meters per second. Now, the other ball is not moving, 0.3 kilograms. Its initial velocity is 0. After the collision, the ball A, which is 0.5 kilograms, is moving upwards at 2 meters per second at some velocity in the X direction. So that we're going to just put 0.5 kilograms V final for A and the X, plus the 0.3 kilograms V final B X. And we'll fill in those X's in a little bit. Now, in the Y direction, neither ball has a momentum in the Y direction. So 0 meters per second. And this 0.3 kilogram, it's absolutely not moving. So it's not. So initially, both balls are not moving in the Y direction. Again, forgot to mention there is no impulse on these guys since there's a elastic collision. Okay, after the impact, the 0.5 kilogram ball has a final velocity for A in the Y direction, and the 0.3 kilogram ball has a final velocity in the Y direction. Okay, so what we need to do is we need to plot out these velocities after the collision in the Y direction. So let's do the 0.5 kilogram ball. And I'll do these over here. So the 0.5, or the mass A ball, actually let's just do this. So this is mass A, and this is after the collision. Point, positive X, positive Y, negative X, negative Y. So it's moving off at a velocity of 2 meters per second at an angle of 60 degrees. So this will be positive 2 meters per second, cosine of 60 degrees. That is V final A X. This will be positive 2 meters per second, sine of 60 degrees. And that's equal to V final A Y. Okay. I'm just going to figure out what those numbers, you know what, I'll write those out. Let's do the same thing for the object B. So I'm going to positive X, positive Y, negative X, negative Y. So after the collision, this guy is moving down and to the right at some final velocity. So VB at an angle that we do not know. Which they said is beta. So this velocity in the X direction, so this is V final B X, this is going to be positive VB cosine of beta. This is going to be negative, well, let's put so it's the negative Y direction, so V final BY equals negative VB cosine of beta. That should be sine. Okay. All right. Well, just double check. This is 60 sine and cosine. V final A, V final A. That looks a little bit weird. in the y direction. This is in the x direction. This is in the y direction. Looks good. All right, let's start putting some numbers in here. So this is going to be 4 times 4 meters per second divided by 2. So that's going to be positive 2 kilogram meters per second. And I'm just going to ignore the 0. This is going to be V final AX, which is this. So this is going to be 0.5 kilograms times V final AX, which is positive 2 meters per second cosine of 60 degrees. And that is going to be equal to, nope, not equal to, plus 0.3 kilograms V final BX. And I'm going to take this and scooch it over. And let's figure out what V final BX is. So this is still positive 2 kilograms meters per second. And this is going to be 1/2 kilograms times 2. So that is just 1. And cosine of 60 degrees. So 60, I think that is a half. And it is. Why do I never trust myself? So when you multiply this all out, it's going to have a momentum of 0.5. 0.5 times 2 times 0.5, so that's 0.5 kilograms meters per second. And that's going to be plus 0.3 kilograms V final BX. All right. We're going to subtract this onto the other side, which we will get positive 1.5 kilogram meters per second equals 0.3 kilograms V final BX. So 1.5 kilogram meters per second divided by 0.3 kilograms. This is the V final BX. All right, so 1.5 divided by 0.3 equals 5. I suspected that, but just didn't. Why don't I trust myself? So this is going to be 5 meters per second to the right. So this ball is going to be moving at 5 meters per second to the right, while this other ball is going to be moving at whatever 2 so 1 meter per second to the right. All right, so we got something that's important here. Now let's do the let's do the y direction. So this is just going to be 0 kilogram meters per second, but this V final A is going to be 0.5 kilograms times 2 meters per second upwards, sine of 60 degrees, which is 0.866, plus 0.3 kilograms VBY. No, that should be V final. So I'll put a final there, V final BY, which is this guy right here. Okay. So this 0, we're going to multiply this through. So that's just going to be 0.866. That's weird. So this is 0.866 kilogram meters per second. So how I got that, 2 divided by 2 is just 1. So whatever the sine of 60 degrees, which is 0.866, that is the momentum, plus 0.3 kilograms V final By. We're going to subtract this onto the other side. So negative 0.866 kilogram meters per second. And while I'm here, I'm just going to divide this by 0.3 kilograms. And this is V final B in the y direction. Let's figure out what that is. In the y direction. Okay, so calculator, 0.866, and making that negative and dividing that by 0.3, and that is negative 28. Okay, hold on 1 second. It took 0.03. That's crazy. 0.866 divided by 0.3. Okay, that makes more sense. Just freaked myself out for a second. So this is going to be negative 2.89 meters per second. Okay, so these two things are important because that's going to allow us to figure out what VB is. Okay, so to figure out VB, so here's where our trigonometry comes into play. This VB is right here. What we figured out in the x direction, this is positive 5 meters per second. And in the y direction, this is negative 2.89 meters per second. So what we're going to do is we're going to do c squared equals a squared plus b squared to figure out the overall speed of VB. So VB is going to, VB squared, we're going to square root both sides, is going to be equal to the x squared velocity plus the y squared velocity. Which we're going to square those both. So we're going to get the velocity in the overall velocity here, 2.89 negative, that we're going to square, plus 25 equals, and then square root. 5.78. So the overall velocity of this is 5.78 meters per second. Okay. All right. Now let's go ahead and try this for the let's figure out what the angle beta is. Okay, so that angle beta, I'm going to do the tangent of beta. That is going to be equal to the y direction over the x direction. So that's and I just want to take I just need the number. Okay, V B y over V final bx. Okay, and then we're going to take the inverse tangent of both those. So what this is going to yield is going to be beta, which is the angle. It's going to be the inverse tangent of the y direction, which we just need the number, negative 2.89 meters per second, I'm going to take the magnitude of that and divide that by 5 meters per second. Okay, and so that angle, 2.89 divided by 5 equals, and we're going to take the inverse tangent of this, 30.02. So 30 degrees. Just going to round up to 30 degrees. So that is the overall velocity for the B guy and its angle. All right. So here's how to handle problems where it's an elastic collision in 2 dimensions. Okay. All right. Something's not right with this problem. I know I did the math correct, but I think the textbook that I got it from, I think they need to check their math on that. But the point is go ahead and try to learn from this approach, this procedure I did, right? And what you're doing, again, through this is you're solving for the momentums as they are 2 separate things. And that involves you taking a perspective only looking in the x direction and a perspective only looking in the y direction and building those equations off of those. Okay? And incidentally, this was traveling upwards and this is traveling downwards. So we didn't know that. The math worked itself out, and there we go. So this is 6.2 collisions in 2D. I hope you learned a lot. Thank you very much. Have a good day.